Hello to everyone and welcome to this Kaeser Compressors webinar. Okay, right now I'd like to introduce today's presenters. First we have Grayson Atkinson. Grayson has a degree in mechanical engineering from Virginia Commonwealth University. As Kaeser's System Design Supervisor, Grayson analyzes compressed air assessment results to find areas for cost reduction and system optimization. Additionally, Grayson is responsible for receiving in-house system drawings and designing systems that follow best practices to meet a wide range of demanding applications and installation challenges. Grayson completed the DOE Compressed Air Challenge 1 and 2 and is a Master Certified System Specialist through Kaeser's Factory Training Program. Now also with us today is Tom Butchers. Tom serves as a Technical Service Representative for Kaeser's Compressors Incorporated, providing installation and service support to field service personnel. With over 23 years in electrical and field engineering support, Tom has provided technical support expertise for a wide range of industries, including semiconductor tooling and static and rotary uninterruptible power supplies, frequency converters, and synchronous generators in the power quality field. He has also served as a data center facilities technician supporting CRAC systems, chillers, UPS systems, and emergency diesel generators before joining Kaeser's Compressors in 2015. Tom holds a journeyman electrical license from the Commonwealth of Virginia and in 2008 completed an inside wireman apprenticeship with the International Brotherhood of Electrical Workers. He is also a 10-year veteran of the U.S. Navy, where he served as an electronics technician aboard submarines. Now, our third speaker today is Neil Mehltretter. As an engineering manager, Neil is a key player in Kaeser's technical department, with responsibilities including product management, system design, and more. An authority on compressed air assessments, Neil has conducted and supervised thousands of industrial compressed air studies, helping users achieve significant energy savings and operational improvements. He has authored several nationally published articles on compressed air system optimization and is a frequent presenter on energy-efficient system design. Now, in addition to his bachelor's degree in chemical engineering from the University of Florida, Neil is Airmaster Plus certified, has completed the DOE Compressed Air Challenge 1 and 2, is a certified energy manager, and is a Master Certified System Specialist through Kaeser's Factory Training Program. So Grayson, Tom, and Neil, welcome to today's event. And with that, I'm going to pass things over to Grayson to get us started. So Grayson, go right ahead.
Thank you and welcome to today's webinar, Best of the Worst, a look at common mistakes in compressed air systems. There are many different items that can affect compressor operation. Several of these are within the original scope of work for the compressor station, and if not addressed properly, they can have a significant effect on the compressed air equipment lifetime and reliability. We'll focus today on 6 of these items: ambient conditions, ventilation, electrical supply, maintenance, oversized systems, and proper controls. Ambient conditions is a fairly simple topic to understand. Where you place your compressed air system often comes down to the real estate available. Often it is limited by where the original compressed air station was located. Regardless of the location, it should be in a clean, indoor, temperature-controlled environment. The picture and graphic at the top right show ideal locations, whereas the pictures at the bottom right show less ideal install locations. Anytime you have equipment exposed to the elements, you have the potential for reducing equipment lifetime due to water, sunlight, or temperature fluctuations. For example, one of the pictures shows a receiver tank installed outdoors. This location was most likely chosen because the tank was too large to fit inside of the building. But if the outside air temperature drops below the compressed air temperature, water can condense in the tank and possibly freeze. Likewise, during summer months, the tank being installed in direct sunlight can further warm the compressed air, which can cause dryers to fail. As you can see from the pictures, care must be taken in not only where you place the equipment, but how the equipment is conditioned to operate. If low ambient temperatures are expected, and this can even happen indoors, care must be taken to ensure that the water cannot condense within the compressor when it is offline. As mentioned in the previous slide, we do not recommend outdoor installations, but the pictures shown give you an idea of how exposed compressed air equipment can be. The harsher the conditions, the shorter the mean time to failure, and the less reliable the equipment will ultimately be. Compressor rooms are often in places most people don't venture. They can also serve as additional warehouse space. The reality is that compressors are a critical part of plant operation, and therefore access to the compressor and ancillary equipment is critical. Ensure that not only does your compressor have sufficient service space, but also that from a day-to-day standpoint, you can easily review operational conditions on your equipment. What goes in must come out. Compressors ingest ambient air, and this air comes out in the plant process. If your compressor room is located near exhaust fumes or other contaminants, those contaminants have an opportunity to be passed on to the end use. Certainly, filtration can be installed to remove hydrocarbons. However, this is an item that must be considered during your design phase. As mentioned before, outdoor equipment is not recommended, but if your facility is near a pasture, you may not have a choice in how the wind blows or the quality of air ingested by your compressor. We'll see more on the effects of ambient heat on equipment when we get to the ventilation and maintenance sections of this presentation. The two pictures at the right show how hot air from neighboring pieces of compressed air equipment can be blown onto one another, increasing operating temperatures and decreasing reliability. This isn't always limited to just compressed air equipment, but can be caused by anything within your compressor room, such as a boiler. Another consideration is whether the equipment will be in an area with a full washdown. If this is the case, then it is recommended to relocate to a different area altogether. With the introduction of variable frequency drive or variable speed drive compressors, control logic and electrical design have become more complicated. This has offered increased potential for efficiency. However, these electronics are more sensitive to heat, moisture, and dust than a standard fixed speed offering. Therefore, before installing a VFD in your plant, consider whether the environment would be hospitable. To sum up the points we've discussed regarding ambient conditions, strive for installations which are located indoors in clean, temperature-controlled environments. It's crucial to have easy access to the equipment. The location of the compressor room is important, as is what other equipment may be placed in the room. Finally, know the vulnerabilities of a VFD prior to installation and consider whether or not your designated install location will be hospitable. Ambient conditions vary based on where you are in the world and may change throughout the year or even day to day. Your compressor shouldn't run below minimum temperature or oil becomes too thick to circulate properly. Condensation can form inside of the compressor, and electrical components can become less reliable. Your compressor shouldn't run above maximum operating temperature, or heat won't be properly removed from the air end, causing it to expand and potentially leading to component failure. Maintenance intervals will be decreased as oil life is shortened, and air quality can also suffer as the approach temperature may be too high. Air-cooled compressors need cool ambient air in order to operate effectively, but where does this air come from? In most cases, it comes from a cooler area of the plant or outside of the plant altogether. It ultimately depends on the location of the compressor room and the presence of any contaminants within the air itself. Are there hydrocarbons in the air outside of the plant? Is there dust, dirt in the air in the surrounding rooms of the plant? The compressor needs cool air for summer operation, and you want this air to be as clean as possible. Using a thermostatically controlled inlet louver damper, like in the picture, allows you to regulate how much of this air enters the compressor room. When coupled with a recirculation system, this provides a degree of control over the temperature in the compressor room, helping you to keep the room cool in the summer and warm in the winter. However, installing a louver damper in an opening reduces the free area of that opening. This is true not only for thermostatically controlled units, but any louver, damper, or bird screen. Free area is the actual, unrestricted area of an opening. Be sure to take this into account when sizing openings in walls. Begin by determining what the free area rating is for the device you're installing, then oversize your opening so that the total free area requirements of the compressed air equipment are still met. For example, if you need 30 square feet of free area for a compressor room, and you're planning to install thermostatically controlled inlet louvers in the room, you already know that the openings you make in the wall need to be larger than 30 square feet. The real question is how much larger. Let's assume you're using a louver with a free area of 50%. This means that for every square foot of the louver, the free area is 1/2 a square foot, and the blocked area is 1/2 of a square foot. If you need a total of 30 square feet of free area for our example, you need to double the size of the opening to account for the blocked area, making the rough opening about 60 square feet in order to ensure that you have 30 square feet of free area available after the louver is installed. Ducting is absolutely critical to having a well-operating, long-lasting system. Compressors generally have a location for cooling air discharge. This is where the air leaves the compressor package and without ducting would enter the compressor room. Disregard the physical size of this exhaust location and size your ducting based on the compressor's cooling airflow, the maximum permissible pressure drop, and any other pertinent information from the compressor manufacturer. The size of the opening is independent of how big the duct needs to be. In most cases, the exhaust duct will need to have a larger cross-section than this opening. The maximum permissible pressure drop value is key. Compressors generally have an internal cooling fan that pulls cooling air into the package and then forces it out again. This fan is in effect both pulling and pushing air. When you connect ducting to either side of this fan, it creates a pressure loss. This applies to the area upstream of the fan, inlet ducting, and downstream of the fan, exhaust ducting. For a given flow rate, the smaller the cross-section of the duct, the larger the pressure loss. The more complex the path of the ducting, bends, elbows, adapters, etc., as you see in these pictures, the larger the pressure loss. The total pressure loss from point A to point Z of the cooling air path should not exceed the compressor manufacturer's stated permissible pressure loss value. To minimize this loss, keep ducting as large, straight, and symmetrical as possible. If your duct is too small or your pressure loss is too high, you won't remove enough heat from the compressor room, temperature will rise, and components may begin to fail. The picture at right shows identical compressors. The compressor at right ran consistently without shutdowns, but the compressor at left shut down frequently on high temperature. In order to test a theory that the left side compressor was recirculating its heat, a temporary duct was installed. The compressor ran 10 to 15 degrees Fahrenheit cooler. Permanent ducting should be installed to ensure proper operation of this unit, as well as alleviate the safety hazard from the temporary duct. Also note that if the compressor room isn't able to bring enough fresh air in, you'll have a negative pressure in the room. This will increase the power consumption, which will not only increase energy cost, but will shorten the lifetime of the equipment. If you do have a space like this, you should consider increasing your airflow, or perhaps consider water-cooled compressors going forward. There are benefits and detriments to water-cooled compressors, and if you're considering making a change, we have reference articles which we can provide that offer more information. Using recirculation as a means of temperature regulation is an energy-efficient way of maintaining the temperature in your compressor room during periods of low ambient temperature. In comparison with HVAC or space heating applications, it's much more energy efficient as it uses heat that the compressor is already making rather than requiring additional electrical input. These systems vary in complexity, but at its simplest, the concept works like a railroad switch, moving exhaust air either down track A out of the room during high temperature periods, or down track B back into the room during low temperature periods. Recirculation involves installing a thermostatically controlled damper in the ducting train of the compressor and linking it to the thermostatically controlled inlet louvers that we've previously discussed. As temperatures increase in the room, the inlet louvers open, allowing cool air from outside of the plant into the room, and the recirculation louvers close, forcing warm exhaust air out of the room via the duct train. As temperatures decrease in the room, the inverse happens. The inlet louvers close, preventing cool air from outside of the plant from entering the room, and the recirculation louvers open, forcing warm exhaust air back into the compressor room in order to raise the temperature. This continues until the desired temperature is achieved and there is a balance. Again, these systems vary in methodology and complexity, but this is the general concept. It requires very little additional energy and does a good job of automating the process. It's typically more reliable than having someone manually adjust dampers on a schedule, and it automatically adjusts as the temperatures do, providing a reliable temperature even when ambient conditions change hour by hour. Be sure to include a backflow damper at the top of each duct train. This prevents cool air outside of the compressor room from backfeeding through the duct when the compressor isn't in operation. This backfeeding could cause room temperature to drop even when the inlet louvers may be closed. It's also recommended to use an analog signal and a proportional controller as an interface, as this allows for variable, finely tuned temperature control. Recirculation is excellent when it's working as intended. However, there are times when compressed air equipment accidentally recirculates cooling air. Typically, this is when the cooling airflow pattern is poorly thought out, or when systems evolve over time and equipment is added bit by bit over the course of many years. We've established that compressed air equipment generally draws cooling air in from its immediate surroundings. This can be a problem if some equipment exhausts towards the inlet of some other equipment. This is referred to as inadvertent recirculation, and it's where the cooling airflow of one machine is accidentally ingested by another machine or the same machine, negatively affecting the temperature balance unintentionally. This was the case in the cardboard duct example we saw earlier, as well as the picture above where the exhaust ducts were dumping warm air directly into the inlet louvers. The best ways to avoid this are to use ducting, employ thermostatically controlled inlet and recirculation louvers, and to have a prevailing direction of cooling airflow whenever possible. Bring cool air in on one side of the room and exhaust warm air out on the other. Having the majority of the airflow in one direction helps prevent accidental recirculation. Try to route exhaust air through the roof when possible, and take prevailing winds and other site conditions into account. It's typically not a problem to exhaust through one of the walls either, as long as the cooling air inlet isn't being pulled into the room through that same wall. If you absolutely must use the same wall for cooling air inlet and exhaust, orient the exhaust so that it's pointing away from the inlet, and provide as much separation as possible. You may also need to install directional hoods on the cooling air inlet openings so that they draw air in away from the exhaust locations. In general, it's best to draw cooling air in from a low location and exhaust warm air out at a higher location. Hot air rises, and this picture is a good example of how to mitigate these issues should they arise. To sum up the points we've discussed regarding ventilation, be sure that you're aware of the equipment's comfort zone per the manufacturer specifications. Compressors put off a lot of heat, and if the airflow in the room isn't adequate, then they won't work properly. Make sure your inlet and discharge openings are appropriately sized. Take full advantage of the heat generated by the compressor and consider recirculation of hot air when useful, but avoid inadvertent recirculation. It's not just your compressor that needs ventilation. Your dryer should also be taken into consideration, as well as anything else located in your compressor room. Now I'm going to hand it over to Tom to discuss electrical supply issues.
When connecting the compressor to the electrical system, make sure all applicable local and national codes are followed. Most places require a facility electrician or other electrically certified party to connect equipment to the building's power supply. It is not as simple as connecting wires and making sure all the connections are tight. Is the wire sized properly? Are the fuses or breakers large enough to allow the motors to start? Is the power supply correct? Is the supply stable? And are all local and national codes and regulations followed? First, let's talk about manufacturer requirements and recommendations. Many times the manufacturer will specify appropriate wire sizes, fuse breaker sizes, as well as the type of power supply recommended for the compressor to operate. These sizing recommendations are based on the National Electric Code, or NEC. However, since most manufacturers are global suppliers, they do not specify any state or local ordinance requirements. This is left up to the electrical contractors or engineering firm that is supporting the installation of the facility. Comparing the actual power supplying the compressor with the manual recommendations can help eliminate and reduce nuisance trips or component failure. Always look at the transformer nameplate. Ensure the output side of the compressor is the correct voltage and configuration. The picture to the right is a compressor with a VFD that was required to be run on a center-grounded Y power supply. The compressor was connected to a non-grounded delta and the RFI filter to the drive blue. Here is an example of a power quality analysis, or PQA study, where the power supply was verified per the manual. However, it was never checked to ensure that there was no imbalance. The compressor was installed and it would only run for short durations. Notice the graph. Measurements between L2 and L3 and L3 and L1 were right in line with each other, while the measurement between L1 and L2 was almost between 10 and 20 volts lower. This voltage imbalance also resulted in a current imbalance, causing the motor to trip out. After tracing all the wires through the facility and inspecting the transformer, it was determined the issue was outside the facility. A call was placed to the local power company to evaluate the incoming power to the building. It was found that one of the transformers was damaged in a storm, and while it was still able to run much of the facility once the larger machines were put online, the transformer could not handle the load, causing the issues with the compressor. Here is another screenshot from the PQA that shows the effect of the transformer problem on the compressor. Notice there are two legs that are fairly close and one leg much lower. This motor is going to run hotter and will burn out more quickly. It will become unreliable over time with frequent motor trips. You will notice that the manual excerpt shown above not only shows the recommended wire size and fuse, but also specifies that 75°C conductors are needed. Many times we see that the contractor used 90°C wire instead. In most circumstances, this is fine. However, there are rules in the NEC on how this can be accomplished. Failure to do so is not only a code violation, but can also affect the performance of the equipment. Pulling wire that is too small can cause the wires to overheat and begin to break down the jacket of the cable. It can also cause heat damage to the breaker, possibly causing nuisance trips. If the fuse is sized too small, the motor may not even be able to start. There are different rules for breakers and fuses, just like there are different types. The NEC has rules for non-delay fuses, dual element time delay fuses, instantaneous trip circuit breakers, and inverse time delay breakers. Applying the wrong device or the wrong sizing rules can be problematic. Here is an example of a facility with a 300 horsepower unit that used an inverse time delay breaker for the compressor. However, due to some installation issues, the authority having jurisdiction told the facility they needed a breaker with ground fault protection, or they needed to make electrical upgrades. This unit had issues starting, and it took multiple attempts each time they wanted to start. They did a power quality analysis and found that at starting, the phases were out of balance or out of phase, and sometimes were more out of balance or out of phase than at other times when it was less. When the measurement showed less, the compressor could start. When farther out of balance, the unit would trip the breaker. They took this information to the breaker manufacturer, and the result was the electronic inverse time delay breaker was calculating this as a leak to ground, even though it really was not. As a test, the ground fault was disabled on the breaker and the unit was able to start without problems. The facility had to turn off the ground fault portion of the breaker and redo the electrical installation to make it meet code. Here is another wiring issue that was found during an inspection process when the machine was to be started. The contractor had selected this welding cable for the compressor as the ampacity was much greater for a smaller size wire, thus allowing for some cost saving during installation. However, there was one slight problem with this cable. It is not UL approved, so the inspector would not let it pass. Looking deeper, this wire is only to be utilized for equipment with less than a 60% duty cycle. This is another example of a shortcut that ended up being very costly. To summarize, when it comes to your electrical supply, make sure you have the proper supply per the manufacturer's recommendations. Make sure the wiring is proper and per the NEC and other applicable codes. Lastly, shortcuts seem to cost more in the end than the perceived benefits up front. Maintenance is a critical component of reliable, efficient compressed air systems. Before beginning a maintenance routine, first assess the site. Is there adequate ventilation? Is it very dirty? Is it humid, hot, cold? Does the compressor match the supply to demand, or is it oversized? If the environment is not ideal, shortening the maintenance intervals allows the compressor to survive in adverse conditions. One can go as far as air sampling for caustic materials, monitor the heat in the room, visually inspect for dirty filters, and take oil samples to see exactly how the oil is holding up over time. It is always better to err on the side of caution rather than push components to their absolute limits. Over the next few slides, we will show you how problems are caused due to lack of maintenance. Before we move on, I'm sure everyone is wondering why there is taffy being manufactured inside of a compressor air end. I would have to agree, it is probably not the cleanest environment nor the best way to make your way into the taffy business. All jokes aside, this actually is the consistency of the oil with the rear cover pulled off the compressor air end. This facility was buying the wrong type of oil to save a few dollars and running it almost twice as long as the recommended lifespan before changing. This attempt to save a few bucks with less expensive oil and doubling the maintenance interval resulted in the loss of production and the replacement of a very expensive air end. Let's focus on the inlet filter and air filters for the compressor. As the air filters plug up, they restrict airflow, which can cause overheating, so making certain air filters are clean should be a high priority. In conjunction with the filter itself, consider the filter housing. If you are changing the filters but the housing is cracked, partially missing, or broken, you are doing a disservice to your machine. Yes, you have this new clean-looking filter. Why is that? Because the housing is broken and has not been repaired, so the majority of air is bypassing the filter and being sucked straight into the compressor. How can that affect my compressor, you ask? Here is a picture of an inlet valve check plate. The user broke his inlet filter housing and did not want to purchase a new one for a few $100s. The customer ran the unit until debris built up so much in the inlet valve the compressor could no longer function properly to make air. The inlet valve needed rebuilt to allow proper operation of the compressor to continue, much more costly than replacing a cracked piece of plastic. Here, a customer purchased non-OEM equipment to save some money. The customer had a technician come out to determine why there was oil in the lines downstream, resulting in lost production. The technician found the separator cartridge to be the cause. When the technician asked the customer how long ago it was changed, the statement was, "a while ago." Not knowing how long something is installed, especially when they have a predetermined lifespan, is not a good maintenance plan. Using knockoff components is also not advised. While it does save money at the time of install, it can cost many times over that if it fails and causes lost production. Know your surrounding processes. Having your compressor ingest clean air is needed for proper operation. However, the question is, how clean is clean? What are you doing in the surrounding area? Any chemical processes? Are there caustic materials? Remember from earlier, the compressor takes in whatever it's in its direct surrounding. This picture of the integrated dryer, notice all the green. This is supposed to be copper tubing. You can see that the environment was eating away at the metal surfaces inside the compressor. Maintenance is not always changing this or adding that. It is about knowing the site and putting the equipment in a location that is stable and will not prematurely degrade any equipment. The actual air compressor, unfortunately, we do not have a picture of it, only lasted another year before being replaced. The cost to repair all the corroded parts, including labor, was more than 3/4 the cost of buying a new compressor, so pick your location carefully. Remember, temperatures that are too cold cause increased moisture, or compressors that have a low duty cycle also require a different maintenance interval. If the compressor does not run long enough to build heat, when it shuts off, all the moisture it sucked in is now trapped. And if you were not certain before, the pictures here show that moisture will destroy an air end. If there is too much moisture, oil changes may need to be increased in frequency, a modification to the unit adding cabinet heaters, sump heaters, or even air end heaters, especially in cold environments where the inlet air is really cold. Not only can cold temperatures and low duty cycles cause rust issues, but so can piping and filtration, or lack thereof. If there are multiple units in a system and one is not running, it is possible for the other compressor to send condensate downstream and make its way back to the unit that is off. Having a liquid separator will reduce or eliminate any water from making it to the compressor that is not running. If the minimum pressure check valve is stuck open or has a leak and water starts to backfill, it will fill up the unit with water and eventually displace the oil, which can cause catastrophic failure. This unit in particular lacked proper filtration maintenance, and eventually the 400-gallon receiver tank filled up with water and a minimum pressure check valve was stuck open due to lack of maintenance and filled the compressor up with water. This resulted in replacement of an air end. Consider that the cost was not just the replacement of the air end. The compressor needed to be disassembled, piping and separator cleaned out, as well as the cooler pooled and set out to be dipped and baked to get all the scale and rust out. Not to mention all the valves needed to be rebuilt as a precaution. Getting back to ambient conditions and dirty, dusty environments that Grayson mentioned, the air filter pictured on the left is from a fiberglass forming company that continually pushed out maintenance due to lack of a backup unit. The air filter on the right is from a facility that packages cocoa. This caused the filter cap to crack and the cocoa powder entered the compressor. When the compressor shut down, it would not restart as the cocoa had mixed with the oil, causing it to solidify into a material that resembled molasses. Changing service intervals would certainly help, while an alternative placement to the compressor could completely address this issue. Let's not forget the driving motor. Many times the greasing is overlooked, not done at the proper interval, or improper amounts were pumped into the motor. Insufficient grease can cause the bearing to fail, the motor to drop, and the shaft contact the windings, making bearing change turn into a rewind and motor dip. The motor nameplate will signify the amount of grease needed for each bearing. However, the interval on the nameplate may not be the same as in the manual. If the environment is hot, dirty, etc., the bearing grease may need to be refreshed more often than the standard manufacturer recommended intervals. Failure to keep grease fresh in the motor will ultimately end up in catastrophic motor failure. Also to keep in mind, not only should the grease interval be monitored, but also the proper type of grease should be used, and the amount of grease per pump of the grease gun should be measured so that the exact amount of grease is known for each pump of the grease gun. The pictures on this slide show various motor failures due to the greasing issues. Heat is also a killer of components. On the left, you can see a thermal image of the cooler. To the naked eye, the cooler just looks a little dirty, and maybe could be cleaned. Further investigation shows the infrared picture. Notice the cooler has a large black spot indicating there is no oil flow going through that portion of the cooler. The picture on the right is a compressor at the same location, just newer. You can see that there is much more heat distribution through the cooler, but it still has a dead spot on the right in black. While this unit definitely can distribute the heat better through the cooler, the unit is still overheating. This site suffered from lack of maintenance. The oil changes were not done as necessary. The oil filters did not get changed until there was a differential pressure alarm on the filter, and good housekeeping practices of simply cleaning filter mats and coolers were not followed. These units were able to be salvaged by running a cleaning solvent through the oil circuit, removing the majority of blockage. The coolers were not 100% effective after the cleaning, and replacement was recommended. In summary, clean your system regularly, visit the compressor room regularly, ensure that motors are greased and oil intervals are adhered to. Always consider the environment. If it is harsh, increase the service intervals. When in doubt, talk to the equipment manufacturer. Baseline your operation with oil samples and adjust service intervals if needed. Thanks for listening to these key points. Now Neil will explain the effects of oversized systems and proper controls.
Thanks, Tom. It's a wealth of information there, so we'll move on here with oversized systems. If the compressors are oversized, they're never going to come up to operating temperature, and there's a good chance that you're going to have a problem with moisture. Therefore, oversizing can also lead to air quality problems. In many cases, a customer purchases a large compressor in order to future-proof the installation, but ultimately the compressor remains oversized, sometimes grossly oversized, for its entire lifetime. This not only costs more to operate from an energy perspective, but also can lead to maintenance and reliability issues, as we've already discussed. Additionally, be careful with equipment that's inherited from a sister plant or something that you might buy from an auction. In addition to not necessarily knowing the condition of the equipment, you really want to make sure you have a compressor or compressors that's correctly sized for your particular needs. Finally, remember that plant demands frequently change over time, so you want to continuously monitor to see if you need to make adjustments. Building systems in a block concept can make any facility stronger and more reliable. If your system is oversized, you'll notice extended periods of time when the compressors are unloaded. You can compare the duty cycle, which is loaded hours versus service hours of the unit, to determine how oversized it really is. While it may seem expensive to purchase new, smaller compressors for an oversized system, the ROI in these cases is typically less than 30 months, and sometimes it could be less than a year. You can work with a compressed air manufacturer to run a simulation of your station and get a clearer picture of what the ROI actually would be for your specific case. As noted here, an oversized unit that is only using 30% of its overall capacity is going to use 80% more energy than one that's properly sized, running fully loaded to meet those exact same demands. So what's it all mean? The numbers shown here on this slide were taken from a random sampling of compressor stations that we monitored via compressed air audits. The average duty cycle of our sample showed that this was less than 50% loaded. This is probably the worst way to run a fixed-speed rotary screw compressor from an efficiency standpoint. Digging deeper into that data, it also affected station reliability, as those compressors that had above a 60% duty cycle were significantly more reliable. Those units had a 50% greater mean time before failure rate, which accounts for unexpected shutdowns. Considering that the average cost of downtime for manufacturers is as high as $30,000 per hour, such an extension is a significant productivity improvement and can provide an ongoing and immediate cost offset. Keep in mind that if the cost of downtime is high, purchasing backup compressors could provide a very quick payback, typically an even better ROI than this multiple smaller compressor concept we're discussing right now. We've talked quite a bit about oversized compressors, but how do you check if your compressor is oversized? So if you run it in a load-unload and you time the load-unload cycles, that's the best way to do it. If the time it's loaded is less than 30% of the entire cycle, you have significant savings potential by switching to a smaller unit or smaller units. You may also notice a few indicators like varying pressure and short cycling of your compressors. Take action, and you'll have less headaches going forward. In summary, to make sure your system is not oversized, it should have a high duty cycle and a low specific power. This will ensure a reliable, efficient system with a stable operating pressure. Let's talk about proper controls. Most older industrial plants grew into having multiple compressors supplying the flow. In many of these plants, the compressors are spread out throughout the facility with no communication between them, which results in a constant tug of war. More units are going to run than necessary at too high of a pressure, and some of the compressors are going to short cycle like we've already talked about. This is going to result in an unstable system operation and system pressure, as well as higher energy cost and increased maintenance costs. Enter a system master controller. A system master controller is responsible for the entire station. Much like a conductor of an orchestra, it makes sure each and every component is working well and as intended to meet the current demand. Its ultimate goal is to achieve the best possible efficiency at all times. Individual compressor controls as well as a system master control are important to optimize plant efficiency. A system master control is going to rely on the information from individual controllers to best optimize the entire station. In general, system design is going to affect how well a master control is going to work. So like we talked about before in regard to oversized systems, if those are split up into smaller units, then systems that have master controllers are going to work a lot better than stations that have larger compressors. Here we're using this slide to just to show the history of development from pressure-based master controllers. From the initial cascade on the left via a pressure band, or really an internal cascade, to a set point based controller with inner and outer bands, and then finally to the adaptive pressure regulation, which you see on the right, and then we'll get into on the next slide. Cascade pressures were necessary in order to ensure that not all of your compressors came online at once. This was a huge advancement at the time because, number one, it ensured the plant didn't get a high demand charge by turning all the compressors on at once for a standard demand, basically like a Monday morning where the system was shut down over the weekend and you had to repressurize the station. All the machines came on, so your demand charge was significantly high there. And then number two, it could rotate your compressors and try to balance hours, so that also helps from a maintenance standpoint with less service trips. As we move farther away from cascade pressures, we see reductions in energy cost as well as maintenance costs, and we're going to get into that here. So dialing into adaptive pressure versus pressure band. This chart shows the difference between a system controller with fixed pressure bands and a system controller using the adaptive control. With pressure band controls, they're going to be fixed pressure ranges programmed, and once the pressure falls below this range, the controller is going to bring on another compressor and may activate timers. So there may be a considerable lag before the next compressor can come online, and pressure may continue to fall. Depending on the number of compressors in the system and how they're sequenced, it's possible that multiple compressors could be brought online almost at the same time. Further, pressure ranges are preset and rarely see adjustments after commissioning, whereas systems are going to change over time, so those bands may not work like they worked in the beginning. With adaptive control, the system is continually monitoring and the controller is continually learning the system and is ultimately able to predict when system pressure may fall and bring a specific additional compressor online in advance. So maybe a larger compressor or a smaller compressor or a VFD, depending on what that demand is. This is going to prevent a deeper pressure drop as it knows what compressors are online, running, loaded, or those machines that are unloaded, and then also know the time it's needed to bring online compressors that are actually off. It may also consider system storage, i.e. receiver tank volume, and into this equation as well. This adaptive type of control can only work effectively because it knows at any time all the data and parameters of all the compressors and pertinent components that are integrated into the system by having what we call a digital twin or replication in memory. So again, design makes a big difference in how well a master controller is going to work. So in the end, what kind of savings can you expect by having a system master controller? With a system master controller, you'll have reduced run and idle time. You'll only be running the units you need, and the starts and switching losses will be reduced as well. This can give savings anywhere from 2 to 10%. Additionally, it will improve pressure performance because it quickly recognizes pressure changes and maintains stable pressure control. This can provide even more savings, up to 10%. Maintaining a stable pressure is important for most facilities. However, trying to maintain too tight of a pressure band can result in short cycling of your compressors, which inadvertently increases operating costs as well as maintenance costs and decreases reliability like we've seen in the previous slides. Therefore, during periods of low demand, an adaptive control may increase the overall pressure band to ensure not only proper cycling of your compressors, but also achieve higher energy savings. Finally, a system master controller can reduce artificial demand. So artificial demand is any time you run your system at a higher pressure than necessary. This savings will vary per system, but keep in mind that you can have a 1% savings for every 2 psi reduction of pressure. So in the end, how do you know how efficient your station is? And that is actually specific power. Specific power is going to explain how efficiently a compressed air system is operating, but it doesn't necessarily explain how efficient the system is. 50% of the compressed air supplied could be wasted energy based on Department of Energy data. Therefore, specific power is only going to explain whether your compressed air station is efficiently generating air or not. Specific power varies based on flow demands and operating pressure, as well as compressor design and station design. Considering multiple compressors with different controls, such as dual control and variable frequency drive, those can have a really big impact on overall station efficiency. So we'll review another key point on the next slide. And that key point here, which you see in the screenshot, is taken from the same graphic as the previous slide. So this master controller is collecting operational data from all the compressors it controls. One of these data points is load versus idle time of each compressor. So we talked about that. That's that duty cycle. Taking a look at compressor 1, we can see that over the selected 24-hour period, that compressor uses about 440 kilowatts for on-load operation. Over that same interval, the compressor 1 only used 8 kilowatts while idle. So if we create a ratio of these two numbers, we see the duty cycle for number 1 was 98%, meaning 98% of the time the compressor was running, it was fully loaded, which is really a great thing. Excellent duty cycle for a load-on-load compressor. Remember what we talked about earlier about oversized compressors. The ROI to replace these units can be significant. Therefore, data points like these from master are very powerful. In this case, all the compressors have a very high duty cycle, which is very efficient. Some additional benefits here with a master controller include remote monitoring capabilities. Keep in mind that most industrial plants are going to have more than one compressor supplying the flow, making a system master controller a really important part of their energy management strategy. Some advanced controllers even have data storage capabilities and can track and calculate specific energy consumption. Some also support ISO 50001 energy management standard, which is a great bonus. Additional benefits are looking at data during off-peak or holiday times. During these times, the plant could see what their potential leakages are and then figure out what the costs associated with those are and address them as quickly as possible. Further, remote monitoring capabilities mean the system information can be accessed from anywhere at any time. Technicians can view diagnostic codes before performing service. That'll cut down on troubleshooting time on site and allow them to show up with the correct parts, which again saves time. In a summary here on proper controls, if your station has a high duty cycle on all compressors, along with a master controller, it can eliminate fighting between all of your compressors. This is going to maximize your specific power and should operate the system at the lowest possible pressure, thereby reducing artificial demands. Further, master controllers should provide reporting and allow for remote monitoring. In the end, master controllers aren't substitutes for properly designed systems, but they can help identify inherent problems with the station. So I don't have to tell you, we've covered a lot of ground here, from ambient conditions to controls. When equipment is running well, we have the ability to focus on plant operation. If you have reliability issues with your compressed air station, this could be due to high temperatures, a dirty, dusty environment, or electrical supply issues. In addition, low duty cycle and high energy consumption could also be the cause of these reliability issues. Without reviewing the whole station, such as ventilation, location, ambient conditions, etc., rather than individual pieces of equipment, you might miss the problem and therefore the solution. Don't forget to reassess your maintenance intervals based on your site conditions, as well as evaluate whether a master controller can improve your system. The best way to understand your system is to look at data. So we have more information under the websites listed at the bottom right, and I want to thank everyone for listening, and now we have some time for questions.
Okay, thanks to all of you. And now let's get to the Q&A. We'll have some time for questions. If we don't get to your question, please note the complete Q&A transcript, including answers we may not have time for, will be posted with the webinar when it goes on demand. Okay, our first question here, someone's asking, it says not to install compressors outside, but I don't have room in my plant. What can I do?
Yeah, great question. So when you're looking around your facility and you're trying to figure out where you can or can't put maybe an additional compressor, or maybe you're putting it into a new facility, you can always necessarily look outside, but you don't have to put the machines outside. You could put it inside an enclosure that would be the preferred method. That way you can regulate the temperature. We talked a little bit about ambient temperatures, and most equipment will run most efficiently between 40 and maybe 100 degrees Fahrenheit. So within an enclosure, you can regulate those temperatures. That would really be the best possible scenario for you.
Okay, great. Thank you for that. The next question here is someone's asking, is it worth it to get a VSD compressor?
So another good question. I think there's probably more backstory to that. But in general, when you're looking at a VSD or a VFD compressor, you're looking at how much more energy efficient are you going to be with that machine. We talked a little bit about with the master controller what that specific performance or key performance index of your compressed air station will be. In general, a VSD compressor will improve that efficiency. However, depending on your demands, it may not be necessary to have. So there's different ways that you could spin it. And in certain municipalities, certain places in the country or in the world, you might also get rebates to put a VSD compressor into your system. And in that case, you can save a significant amount of capital costs from it. In general, service-wise, you're probably about the same, maybe a little bit more. But if something does go faulty with a drive or something like that, then it can be very expensive. So you also want to be particular about what kind of power you have. Also, dusty, dirty environments will also affect the VFD compressor as well, maybe more so than a fixed speed compressor. So those are the things that I would look at. In general, I would say typically yes, it can be worth it. But it depends on what the demands are, and it depends on what your capital costs are as well.
Okay, thanks again for that. Another question here: why does my compressor keep overheating?
Hi, so this is Grayson Atkinson. That's actually a really good question, and there's a lot that could go into that. You could have potentially a problem with the machine. It could be that something isn't operating the way it was designed to. You might have a clogged cooler. There could be something wrong with the internals of the machine that are limiting the airflow and the cooling. But more than likely, it's something wrong with the room. We touched a lot on ambient conditions and room design and cooling earlier on in the presentations. And the main thing is you've got to know how much cooling air that machine needs, and you've got to be able to get that air into the room and that warm exhaust air out of the room. And typically for larger machines, ducting is the best way to do that. You got to make sure that the ducting is adequately sized and that it's exhausting away from the inlet location. If you can get enough cool air into the room and enough warm air out of the room, you generally don't have any problems with your installation. The flip side to that is, maintaining a cool, adequately warm temperature in cooler months. And we went over that a little bit in the presentation as well, but it's all got to be thought about up front. And if you've never had a problem before and everything's been great and all of a sudden something's developed, then maybe it's something wrong with the machine. But if this is an issue that's been around the entire time, it could be something with the room design.
Okay, thanks, Grayson. Another question here: how can I tell if my compressor is oversized?
Yeah, so this is Grayson again. Really, you've got to look at the system as a whole. If you're having multiple machines loading and unloading at the same time, if they're fixed speed machines, or you've got a variable speed compressor that's ramping up and ramping down at the same time that a load-unload machine is starting and stopping, that's a good chance that there's some kind of control issue. Storage comes into factor as well. If you've got an adequately sized compressor with not enough storage, you can still see some rapid cycling. So that doesn't necessarily indicate that the compressor is oversized in and of itself. But the main thing I would say is if you have a very variable demand profile, low demands at one point of the day, really high demands at other points of the day, and you've got one single compressor that's a fixed speed unit that's attempting to cover all of those different demands, there's a good chance that it's at least partially oversized for part of that demand profile. And we touched on that in the presentation as well, but it really does lend itself to maintenance issues and potential failures later on down the road.
Okay, moving on to our next question. What are the most important design considerations within a compressor room?
Yeah, so this is Neil. I'm going to start off and probably hand it off to Grayson or Tom. You know, it's a tough call. You know, it really depends on the day. If you've had difficulty with one thing like ventilation or overheating for your compressors, you know, that's going to be your most important thing. You know, other things are going to be accessibility. You know, how easy is it to get to the compressor? How easy is it to turn it on and off the unit? You know, also data analysis is interesting because you don't necessarily have to be in the compressor room to get information, so you can stream that through web services and others. You know, so from a design consideration, usually for me it goes back to what Grayson just said about, you know, maybe you have one machine covering the entire demand. You know, typically from a stepwise configuration, you know, multiple blocks, like when we were kids, you just have smaller machines to fill demands. You know, that really lends to, well, what is my demand? Because we've talked a little bit about it here with the question and answer, but if you don't know how much air you're using, you should probably have an air audit done. A simple way to do that is just a load-unload cycle time. And, you know, like Grayson alluded to the last question, look at it at different times of the day because you might be using more air, you know, right before lunch or right before shift change. So, you know, you can get an idea on a duty cycle just easily through that. And then you can kind of figure out, you know, okay, what do I need? And then look at the pressure profile as well. So, you know, that'll expand to the room, you know. So if you say, oh, I only have one machine, that's the only thing I can put there. Well, it might not be the most efficient. So now you might need a little bit more space to put those compressors in addition to the ventilation, in addition to the accessibility. You know, lighting's also something that, you know, we kind of joke about, but we've also seen where, you know, compressors tend to be put away and not necessarily thought of until you don't have compressed air. So, you know, there's a couple of different considerations that I'd look at.
Yeah, this is Tom. I would say from a non-engineer's point of view that the biggest consideration I would suggest is accessibility. I don't know how many times I've been in places and you're trying to work on something and they've got a compressor or whatever piece of equipment jammed into a corner up against a wall, and you have absolutely no way of actually getting in and fixing that, you know, conveniently or even safely sometimes. So other than lighting, which is very, very important, accessibility is my biggest point.
So I think these guys really hit the nail on the head. To sum it up, in my opinion, you've got to know for a greenfield installation where there's no existing system, which compressors you're going to use and which air treatment you're going to use, and figure out how much space that's going to take. And then once you know how much space it'll take, you know how big your room is, you've really got to look at the cooling. Where are you going to pull air in? How are you going to get heat out? And to me, that's the most important thing that goes into the room design is A, will everything fit? B, can I work on everything? And C, can I maintain a good temperature within that room?
Okay, great. We're going to wrap the webinar up right there. Thank you to our presenters for spending some time with us today. And thank you to all of our audience members for being a part of this webinar event. Take care, and we'll talk with you soon.